Good morning one and all. Present over here. I am Hina Gupta from Department of Mathematics. Today we are going to discuss Unit First. The name of Unit First is Sets, Relation, Function and Theorem Proving Techniques. The topic on which we discuss today is Mathematical Induction and Pigeonhole Principle. So, in these two topics we will discuss today one by one. Here are some outlines of this video. First is prerequisite of topic, second one mathematical induction, third one example based on mathematical induction, prove by contraction, after that pigeonhole principle, example of pigeonhole principle, exercise on that topics, learning outcomes and references. So, these are the outline on which we discuss today one by one. So, let us start our video. First is prerequisite of topic. So, which is most important topic for this video? First is a statement. You have a basic knowledge about statement. When we say statement is true, when we say statement is false, so this is the, you have to have basic knowledge about statement. Second, set theory. What is sets? What is well defined set? Types of set. So, you have a basic knowledge about set also. And the last is basic knowledge about mathematical formula. So, you have a basic idea about these topics. Now, real life example, where we use mathematical induction in real life. The first point is, there are a lot of mathematical theorem that can rely on your everyday life, which may have been proved by induction. It means that a mathematical theorem can be proved by the induction. Second one, practical example where we use mathematical induction. We use mathematical induction in factorial or any recursive equation that can only be solved by mathematical induction logic. With the help of mathematical induction logic, we have to solve the problem which is based on factorial. After that, third one, we use mathematical induction for proving many complex problems, either which is based on software developing, basis on database and etc. And the last one, we use mathematical induction for generalization. This is important. If we have to generalize any statement, any result, so we use mathematical induction for that. So, this is a real life example which is based on mathematical induction. Now, definition of mathematical induction. What is mathematical induction? A certain statement or formula or theorem Pn, P of n, is true for all n belongs to n, provided first it is true for n equals to 1. You have to prove first any statement for n equals to 1, that is P of 1 is true. The second point, it is true for n is equals to m plus 1 whenever it is true for n equals to m. That is, P of m is true, which implies that P m plus 1 is true. If we replace m by m plus 1, then it is also true for P of m plus 1. So this is the mathematical induction. Now another form of mathematical induction. We can also say complete induction is just as similar to mathematical induction. Let P of n be a statement or formula or theorem defined for all n belongs to capital N such that P of 1 is true. You have to prove the statement, the formula for P of 1 for putting n equals to 1 in that formula. After that, P of n is true whenever P of m is true for all m which is greater than or equals to 1 and less than n. Then we can say P of n is true for every positive integer. So these are the two statements for mathematical induction. Now example based on mathematical induction, by which you can easily understand. Now example number 1. In example first, a series is given. In this series, (1.3) plus 2.4 plus 3.5 and dash to n plus 2 is equals to 1 upon 6 n into n plus 1 into 2n plus 7 for all n belongs to capital N. So you have to prove this example with the help of mathematical induction. Now solution. Let P of n is equals to 1.3 plus 2.4 plus 3.5 and so on plus the last term n plus 2 is equals to 1 upon 6 n plus 1 2n plus 7. Now first we have to prove this statement for n equals to 1. So you have to put the value n is equals to 1 in this statement. After that you get P of 1. If you put n equals to 1 in this statement, we get P of 1 is equals to 1 into 3 is equals to right hand side we get 1 upon 6, 1 into 1 plus 1 into 2 into 1 plus 7. So you can check here, both LHS and RHS are same, are equal. Thus, this statement is true for n equals to 1. Thus we get P of 1 is true. This is the first step. Now come to second step. Assume that P of n, the statement, is true for n equals to m. In second step, you have to assume this statement is true for n is equals to m. Now we have to check this statement is true for n is equals to m plus 1 or not. Clear everyone? In second step, you have to assume the given statement is true for n is equals to m, and after assumption you have to check that statement is true for m equals to 1. If it is true for m equals to 1, then it is true for all positive integer. Now Tm plus 1, because it is true for n is equals to m. Now we have to prove, now we have to check this statement is true for m plus 1. Now P of m plus 1 is equals to P of m plus Tm plus 1. The additional term is the sum of m plus 1, which is equals to Tm plus 1. Now P of m, putting the value of P of m, the value of P of m is equals to 1 upon 6 m into m plus 1 into 2m plus 1 plus. Now putting the value of Tm plus 1, we have to replace m by m plus 1. After replacement we get m plus 1 into m plus 1 plus 2. Now we have to solve this. 1 upon 6 is equals m plus 1 into 2m plus 1, and if we solve this we get m plus 1 into m plus 3 is equals to 1 upon 6. Now take m plus 1 common, because in both the term m plus 1 is common, so we take outside m plus 1. The remaining is left in the bracket m into 2m plus 7 plus 6 m plus 3. After that, which is equals to 1 upon 6 m plus 1, you multiply m into 2m plus 7, we get 2m square plus 13m plus 18. We get finally a quadratic equation in m. Now you have to solve this quadratic equation by middle term splitting. After using middle term splitting, the quadratic equation is split into two factors. First one is m plus 2 and the second one is 2m plus 9. Now you have to write these two factors in the certain form. M plus 1, we can write m plus 2 in m plus 1 plus 1 and 2m plus 9 in the form of 2 in bracket m plus 1 plus 7. Now you can see here this statement which is true for n is equals to m, and it is same as if we replace m by m plus 1, we get same result. Thus the above relation show that P of n is true for n is equals to m plus 1. Therefore, P of n is true for all n belongs to capital N. So this is the example which is based on mathematical induction. Now come to second topic, which is proof by contradiction. Suppose the statement says that we want to prove a statement. Sometimes it is convenient to prove by its contradiction. There are so many theorems which can only be proved with the help of contradiction. In contradiction, we assume that the contrary of the statement is true, and then by arguments we prove that it is contrary to our assumption. Hence, we say that given assumption holds. In this contradiction, we assume that the statement is true, and after that arguments, we prove that the contrary of our assumption. In this way, the given assumption hold. We can say it's true. So, in this way, we use this contradiction to solve many complex theorems. Now, the last topic of this lecture is the pigeonhole principle. The statement says that if the number of pigeons, we can say its object is more than the number of pigeonhole, that is boxes, then some pigeonhole, that is boxes, must be occupied by two or more than two pigeons, that is object. In other words, we can say if number of pigeons is more than the number of pigeonhole, then some pigeons must be occupied one pigeonhole. So, this is the statement of pigeonhole principle. If we relate this principle by set theory, in set, if A and B are two sets, two non-empty sets, such that cardinality of A is greater than the cardinality of B. The cardinality means number of elements present in the set. If number of elements in set A is more than the number of elements in set B, then a function f of A to B can never be 1, 1, because we know about 1, 1 function. Every element of A is related to a unique element in the set B. But according to this situation, number of elements in set A is more than the number of elements in set B. So, there exist two elements in set A. We have given name also A1 and A2. Both the elements in set A must be it's related to only one element in the set A. In other words, the images of A1 and A2 in the set B is same. It can also be written in A1 comma A2 belongs to A such that f of A1 is equals to f of A2. The images of A1 and A2 is same. So this concept, the pigeonhole principle, is also called Dirichlet drawer principle or shoebox argument. So this is pigeonhole principle. Let's come to its example. If a company has 13 employees, then show that at least 2 of the employees were born in same month. So this is the question. Now come to its solution. Let us take of 13 employees are pigeons and we are having only 12 months, January, February, March, April, May and to December. So we are having only 12 months, but the employees is 13. As the pigeonhole principle, there are at least 2 of the employees were born in the same month. It is quite understanding. If a company having 13 employees, then at least 2 of employees were born in the same month. So this is the example which is based on pigeonhole principle. This is the exercise for you, in which I have given 2 questions. So you have to do exercise. Learning outcomes. What we have learned from this video. In this video, we understand the concept of mathematical induction. By which we can prove other statement as well as theorem. I have said that with the help of mathematical induction, we can solve many complex problems, many complex theorems very easily. Because mathematical induction is used for generalization. If we want generalization of any theorem, we apply this mathematical induction. From second topic, we understand the concept of contradiction. It is also very helpful for proving some complex statement, complex theorems. This is the another way for solving such problem. Now third one, to understand the concept of pigeonhole principle. In the last topic, we understand about the pigeonhole principle. We also understand this principle with the help of set theory. So these are the learning outcomes of this video. Here are some references which I have used in this video, and these books are very important. It gives a detailed knowledge, all basic concept about discrete structure. In the last, this is my last slide. Thank you for everyone for listening me. I hope you got the concept of 3 topics. In the next video, we will discuss about the partial order relation, so keep watching. Thanks once again.